Oh, okay, all right, thank you. So, yeah, last time I think I ended by reminding you of some basic facts and earlier estimates about index of minimal surfaces in S3, and I stated the theorem which we're going to look at the proof today. So this is the computation of the Morse index and the nullity for a certain subfamily of the Lawson surfaces, a family in which every genus is realized. So remember, for minimal surfaces, an estimated Jacobi operator, which governs the second variation of area, is Laplacian plus the square norm of the second fundamental form plus 2, coming from the Ricci curvature, and the index is the number of strictly negative eigenvalues of L or minus L, depending on your sign convention, but basically the number of directions which will drive the area down, while the nullity is just the dimension of the kernel. And so our theorem gives the index of CG1 in terms of the genus, and the finality is 6 for all of them. We're assuming G is at least 2, so that we're excluding the sphere and the Clippard torus. Okay, but you know that the notation that Nikos and I use is a bit different from the Lawson one. Instead of using the genus, well, because this parameter is fixed, G really is just the genus here. We like to use this parameter m, which is shifting from the genus by 1 in this case. So I'm going to do that, and then the point is that 2m then gives you the number of points of these Lawson surfaces on the great circle C. Well, in this family, we always have 4 and so forth. Okay, so that's the family we're looking at, and this is the goal, and well, this is well the nullity. Okay, and so what are the elements of the strategy? Okay, well, I'll mention 2, and then I'll be much more specific. So first, the thing is that we have a bunch of eigenfunctions for free right away. So we have namely, we get the Jacobi fields, so the eigenfunctions with eigenvalue 0 that come from the ambient filling fields. And you take some ambient killing field K, you take the inner product with the normals of the surface, a choice of normal, and you get your Jacobi field J. We looked at one such Jacobi field when we were talking about the uniqueness of the disk, the Lawson disk. We looked at the rotations along the axis. Okay, and so we have such Jacobi fields, and the idea is to study their nodal domains. And use that to get information about the index of the nullity. And we're going to use all of these geometric Jacobi fields. In the sense that we'll work with a basis. Yeah, so I have a 6-dimensional space of killing fields, and so you can pick a basis for those, and those will induce Jacobi fields on each of these surfaces. And the Jacobi fields will each one is going to be labeled with a circle. Yeah, so these are the notation is such that this is rotation. So look at this one. This is rotation about C. So I fix C, or equivalently, along C. And similarly for all of them, so I've these circles, I've used this notation throughout C and C per. These other circles, I'll draw a picture to show you. But the point is that these are, I guess, in terms of our four, these are these come from the rotations 6 coordinates. Okay, so we have C, so JC. JC comes from the killing field, right? So JC is a function on the surface. I'm not sure the surface, but the killing field is the one which does those rotations, or equivalently rotations along C perp. JC perp, right? So here's C perp. So JC perp is going to give you rotations along C. And what about these other circles? So the circles are C with some lower label and upper label, and the lower label is telling us it labels the intersection of this circle with C, the upper one with C perp. So these remaining four circles will be orthogonal to C, mutually orthogonal to C and C perp. And they're going to be chosen like this. So I take my C00. And so in the stereographic picture, it lies in, say, the equator. And, you know, I'm just drawing the picture without the Lawson surface, but so to get a basis, I can position these anywhere, but it's going to be convenient to pick this to be align the surface in a way so that this is going to be an axis. So remember, we have this partition of S3 into these tetrahedra, and in half of them, you have a Lawson disk, and the union of the disks gives you the surface. And we have these bisecting spheres, which are spheres of symmetry for the surface. They intersect along the great circle, which is an axis. So we have that. And then, so rotations about C00 will be rotations which fix this circle, and rotations like this, rotations in the complementary circle. We have also the circle C0 over 2 intersecting C at the same point, well, pair of points also the antipodal point, and intersecting C perp at an angle of a point pi over 2 distance from this one. Okay, and then we have the orthogonal circle. So the orthogonal complement, for example, of C, orthogonally complementary circle is going to be the circle C pi over 2, 0, and that circle is going to be 0. Okay, and then there's the other circle, which the picture is already quite messy, but then there's a sixth circle, which is going down through here. So C 2, which is the orthogonal complement of the circle C00. Okay, so we have all those circles, yeah, and again, the notation is that we're talking about the Jacobi field, which is induced by the killing field, which fixes the circle in the notation pointwise and does rotation in the orthogonal circle. Okay. Okay, so part of the strategy, right, very vaguely, is going to be to use those. We have all those Jacobi fields. We can try to study them as we did partially in the uniqueness proof, and see what we can get from those. And in doing that, to complement that, another important piece of the strategy is to subdivide this eigenvalue problem on the closed surface, and we're going to subdivide the surface in various ways to get some eigenvalue problem that we can understand using the information about the Jacobi fields, but also in the opposite direction, piece together to recover information about the global problem.
So there will be points and secret.
So the umbilic points
in the secret are the 4 points, right? Yeah.
So the umbilic points for the surface are going to lie in C. Yeah, and they will actually be, so I didn't draw it, but I said this is going to be picked to be an axis. So actually the umbilic points are going to lie on either side. It will bisect the umbilic points. So if you take the segments that join the umbilics, and these will be bisectors. Okay. Yeah, I'll draw some more when we start looking at these domains. I'll draw some more pictures, and hopefully make it more clear. Yeah, problems on subdomains, which are going to be natural or suggested by the symmetries. And there's sort of two types of subdivisions here. One is we have a composition. Which I'll just a second. Okay, and the other very different type is going to be a decomposition using eigenvalue bounds in the style of Young and Ross. Okay, so let's look at, so we'll do everything, but let me dive into A a bit more. Okay, so just some notation just to match. Again, I'll try not to use too much notation, but when I do, I'll try to match the paper. So actually, I think the definition maybe is slightly different in the paper, but it doesn't matter here. So B is going to be the Sobolev space, the usual L2 Sobolev space on M, right? So my Lawson surface M, CG1, whatever, and we're looking at. So Sobolev space with one derivative. Okay. Now we have, yeah, so remember we did the Lawson construction. We started with these various tetrahedra, and we solved the plateau problem and all that. But we have the bisecting spheres for the tetrahedra, and there are spheres, a family of spheres which is vertical. So in this picture, it goes through C, and then there's a family of symmetry spheres which are horizontal going through C perp. And in the case when K is equal to 2, right? So K tells you the number of wedges or chambers in this direction. So we have just 2 spheres of symmetry. So we have 2 vertical spheres. So 2 because K is 2. And vertical, I mean, okay, and what are they? Well, let's call them, so again, matching the notation of the paper, sigma 0, sigma upper pi over 2, so the upper labels tell you where these spheres come C perp. So here's C, and yeah, let me draw the mark the points on C. So the umbilicus are some 2 points on C, and I'm going to cut now with sigma 0. So sigma 0 looks just like a vertical plane. That's with the z-axis over the stereographic coordinates. And what will the intersection look like? So this is a sphere of symmetry. It cuts the Lawson surface into two pieces, and the intersection I'm going to have curves like this. Okay, and because of the kind of checkerboard pattern or whatever, right, the even odd tetrahedron that we have, the intersection will look like this. But then I'm not going to add anything in here. So instead, I'm connected through another circle, not shown now in this guy. So this is sigma 0. Okay, and so on like that. Okay, but I'm going to cut again. I'm going to cut by both of these spheres of symmetry. And so if I cut also by sigma upper pi 2, this one. Okay, and now I'm going to let me just look at what I get in this quadrant. So then I'm going to have arcs joining like this, and so on. Okay, so these guys, so I have minus these guys. Four components. Which is a disk. So I have this one boundary, and then also, so just I don't know, to build the picture, I have the great circle segments, and they all. So let's see in this quadrant. So here's maybe C per something like this, and there's just 1 point in this quadrant. So there are 4 points of the surface on C per, and so in this quadrant I have just 1, and all of these great circle segments go to this point. So I've got this disk. Okay. Yeah, okay, and these are, both of these spheres are symmetry, so I can, and they commute also, as a reflection through sigma 0 and sigma pi over 2 commute, and so I can do kind of a double decomposition of V. So V, remember, is just the space of test functions, the Sobolev space. So we can do the decomposition V V minus, so this is even. Under reflection through sigma 0. Okay, but again, because I have this other symmetry, it's orthogonal, the symmetries will commute, I can do a further decomposition. That's, so I can decompose each of those into 2 spaces, the even and odd with respect to the other spheres. Okay, and importantly, so because these are symmetries for the surface, they're also going to be respected by the Jacobi operator. So L, Jacobi operator, leaves these spaces invariant. Etc. Okay, so that it's natural to define, and we can talk about them. I use the notation, I'm gonna abuse the notation quite a bit maybe, but then, so before I wrote index for the surface, now I'm gonna apply to the function space. But the point is that I can restrict the Jacobi operator to the space of functions with, some set of symmetries and look at the number of strictly negative eigenvalues, and similarly for the nullity, and so on for the various four subspaces. And so the idea then is going to be to try to tackle these pieces separately, and then you can just sum. All right. Okay. And so what are we going to show you? So I erased the index that we expected, but we show. And we'll look at most of these pieces, at least schematically. We're going to show you the index of plus. So most of the index, at least when M is large, you can say comes from this conjugate, is from corresponds to the subspace. Be one. Okay, so actually, because we have also the great circles of symmetry.
So the genus was M as well, right?
Exactly. Yes, exactly. Yeah. So we'll give you a check, but yeah. So the index of these two subspaces, there's going to be a symmetry which exchanges the problems because we have reflections through great circles, which will trade those two series of symmetry. So this is immediate, the fact that you can follow here, but the computation is going to be that this is one, well, the nullity. Going to be 2. Yeah. Okay. So summing. Okay, so if we sum the index, we get 2 minus 1. Plus 1 plus 1. Plus 2. Oh, sorry, the 2 is for the nullity. That's not right. Okay. Yeah, so 2 minus 1 plus 1 from each of these plus 1 more. Okay. So plus 1 plus 1 plus 1. So there. Plus 1. Sorry. Okay. Okay, let's start now with B minus minus. Okay. Right, so B minus minus. Yeah, and so one thing which I should have pointed out, and we'll look at B minus minus, but that, let's see. So this is a problem which is, yeah, as defined, it's posed on the entire closed surface, but we impose symmetries, but that's equivalent to a problem on a subdomain. So on a single component up here, so I should name one of these components. So it's called so the plus is because we're referring to the fact that we're cutting by these two vertical spheres, and the star is because later on we can do more cuts. And we're not doing it yet. Okay. Okay, so if I look at this eigenvalue problem, but now I introduce this boundary, but with clear data. Because the odd symmetries give you that data, and conversely, if I have an eigenfunction with Dirichlet data, I can extend very functional. Okay, so I can just as well consider that eigenvalue problem. Okay, so again, we're looking at a disk like this, and we're going to use the Jacobi fields, which are rotations. The Jacobi field coming from the Jacobi fields, which generate the rotations about C. The orbits look like this, and you can see that the orbits orthogonally intersect the spheres of symmetry. Okay, but the spheres of symmetry are going to preserve the normal to the surface, and so we can see that this is going to have the correct boundary conditions. So the symmetries. Satisfies the boundary conditions or equivalent, because actually it's right. So Jacobi field on the whole surface, it belongs to P minus minus. Okay. Good. JC is positive. Okay, so in the uniqueness proof, the proof of the disk, we looked at a different Jacobi field, the one with rotations along the axis, and we were looking at just a single disk, and we showed that we had graphicality, that the orbits intersected just once, so any orbit's going to hit that disk in that case, and at most one point. Here we have a similar plane, but we have graphicality, so in fact we have with respect to the corresponding Killing field, in the sense that these orbits are going to intersect at most once, and that's going to imply the non-negativity of the Jacobi field. Okay, and the argument for that is, again, a maximum principal argument, but it's in the style of Alexandrov. Yeah, so again, I have my 8 circle segments on on here. And so what I'm going to do is I'm going to look at a region which is bounded by just two such great circle segments. And if I were to do reflection through, say this sphere, then I'm going to get a Lawson disk. So let's look at the Lawson disk actually. So this is Lawson quadrilateral. Okay. And the spheres of symmetry, right? So the spheres of symmetry that are appearing here as giving us the boundary for this n plus plus star star. Those we have the bisecting sphere here. Maybe this, depending which one I pick. So maybe this is sigma over 0 bisecting. That's the this tetrahedron omega. So I have the Lawson quadrilateral, and I also have this tetrahedron, right, where the faces are at this spherical triangle, in the front, the back spherical triangle, and then the top and the bottom. Okay, and so this sigma 0 bisector is also through C, and it's halfway between. It bisects the front face and the back face. Okay, and we do Alexandrov moving. But we do it with a rotating sphere. So the claim is that we have graphicality, so we claim Lawson disk. Yeah, so the disk that I get, remember what I solved with this plateau data in that tetrahedron, that gives me the Lawson disk. And we claim that this disk is going to be with respect to the rotations about C. Well, not the whole thing. That's definitely not true as stated, because I have this sphere of symmetry. And so if I have an orbit intersecting on one side, it definitely intersects on the other side. But the claim is that it is on each side. So I should have said each half of this. So if I cut the Lawson disk by sigma 0, so I cut it by one of these arcs, say, then I get two pieces, and we claim that each half is graphical. Okay, and the idea for that is, yeah, I won't go through all the details, but it's a rotating sphere, moving plane kind of argument. We start with the front face. The front face, I mean this triangle here, which is the front wall of that tetrahedron. And I know that the intersection of the surface there consists of just these geodesic segments. And I know that the intersection is tangential away from, sorry, it's not tangential except for at these quarter points. So we have graphicality. Near this intersection. So what we do is that we rotate that C. like in the Alexandrov moving plane argument, we're going to reflect the portion of the surface on one side to the other side. The front side to the back. The front being this part. Okay, and so if there were a failure of graphicality before you reach, so if we had an orbit which intersects D at 2 points on the same side of sigma 0, then you would be able to find a point where you're going to have interior contact of the two pieces of the surface after you do reflection. Using this this style argument and the maximum principle, you would have another sphere of symmetry. Another sphere of symmetry through C. But we know we've determined the symmetry group of the Lawson. We know that there aren't any more. And one way is because we know the umbilicus. So we know the only series of symmetry we have are the bisector and the orthogonal one, which is disjoint from that tetrahedron, except for long C. Okay, so it's another maximum principle argument, but using the Alexandrov style argument with reflections. Okay, so this tells us then that we do have the graphicality, and that gives us the sign on JC. It gives us a sign, so the argument is done in just the tetrahedron, and we have graphicality on one side, but then you can generate this n plus plus star star by doing reflections through these edges, say. And you get the surface, and the graphicality will persist. So in fact, you have graphicality from this plane up until sigma upper pi over 2 on the other side. Okay, so we get issues. Okay, so JC is in the function space that we're looking at, and that satisfies the Dirichlet condition. I've already said, and it satisfies. Okay, so it has to be a first eigenfunction. And because it does not change sign. Okay, and so this tells us then that the nullity is 1 because we have this this eigenfunction. It's the first eigenfunction. The next eigenvalue must be positive. So the nullity is exactly 1. And the index is 0. Okay, so let's look at D++ next. D++ at least. Okay. Okay, so for B++, we're going to need another tool. So I mentioned earlier that we do we make these various decompositions. One is like the one I showed with the cutting by the vertical spheres of symmetry, but we also have to do further decompositions in the style of Montiel and Ross. So let me introduce that now. It's used not just for B++, but for several steps in the argument actually. Proposition. Okay, so these arguments were first used in studying the index of complete minimal surfaces of finite total curvature in R3, but the arguments are very general. They can be applied generally to Schrodinger operators much more generally. So let's look at it now. Let's see. Yeah, so I won't try to make precise statements, but let's see. So the idea is we have some domain U, and we have some operator, which for us is going to be the recovery operator. There could be some Schrodinger operator. So U is some domain and some manifold, and we have some boundary data. So we're given the domain, we're given the operator, and we're given this is well, let's just say this is our Jacobi operator, and we're given also boundary data. So the boundary data could, for example, maybe we have the Neumann condition. Maybe there's a condition on this piece, it doesn't matter. Okay, and we also have some decomposition or partition, let's say. U into subdomains. And I won't be precise about it. It can be yeah, quite general, but let's see. So, okay, so maybe something like this. Again, and the proposition is going to give us upper lower bounds on. Actually, again, it's more general, but let's say the index of U with the given boundary data. And to do that, we look at boundary value problems on the subdomains. So we get in terms of the eigenvalues for boundary value problems on subdomains. And sorry, I switched from U to omega. Let me stick with U. I was using omega for the tetrahedra. Okay, so domain U and subdomains U1 through UN. So for the lower bounds, so what's the boundary data we put on the subdomains? So keep both for the upper and lower. We're going to keep the given external boundary data. So this is U2. So the external boundary data is where the boundary of U2 coincides with the boundary of U, so the name of the boundary of U, so here external. So we keep the Neumann condition here and play here, but on the internal boundary, the rest of the boundary. Here impose zero play condition. Well, for the upper bounds, we're going to look at instead on the internal boundary, we put the Neumann condition. Okay, and then we get our bounds. Bound. Okay, so the index of U, and I mean with the given boundary data. On the right-hand side, I have the index or the index plus nullity on the subdomains, and I put a D subscript to mean that I have to supplement, right? I have the given boundary data on the external part, but on the internal parts, I put the zero play condition, like I indicated. Okay, and instead with the upper bound, we use the Neumann, the Neumann eigenvalues, or partial Neumann eigenvalues. Okay, so I won't give the proof, but these are the bounds that we'll use. And actually, yeah, as I said, they're more general. So here, the index is the number of eigenvalues below threshold 0, and the nullity is at that threshold. And you have these statements also if you replace the threshold of 0 by any real number, actually. So you can get bounds on the number of eigenvalues below some given threshold, with the corresponding threshold used on the right-hand side. Okay, and the proof is similar to the proof of the nodal domain theorem. In fact, you can derive the nodal domain theorem using the lower bound once you know that the nodal set is reasonably well behaved. And so another tool which I think of as in the same category, very much the same ideas, is the special case of the Courant theorem. So we'll just use the one case of it. Yeah, so we've already used the fact that the first eigenfunction is going to have a sign. Any higher eigenfunction will have to change sign. So the number of nodal domains, or if you take an eigenfunction, you cut out the nodal set, the domains, the connected components you get are the nodal domains, and for any higher eigenfunction, you'll have at least 2. But in the case of any second eigenfunction, you'll have exactly 2, because you could use this lower bound. So the case that I'm going to use is that any second eigenfunction. I'm looking again at the Jacobi operator, say, on some subdomain, and I have some given boundary data, boundary conditions, any second eigenfunction. Okay, so we're going to need these bounds and also this closely associated factor. So yeah, and not just for V++. So that those are the statement of these tools, but now we'll get back to V++. Okay, so we'll apply this these bounds of Montiel and Ross to the V++ problem. So equivalently to or I can look at on this disk the eigenvalue problem with Neumann data. Okay. Okay, so that's my U in terms of the proposition. And how do we get the subdomains? We're going to cut now by the horizontal spheres. So K equals 2, so we have just the two vertical spheres of symmetry, but we have M horizontal spheres. So horizontal meaning C perfect, and intersecting C orthogonally. So those are the other bisectors. Those contain the other bisectors of the Lawson tetrahedron, and so they're going to cut through something like this. Yeah, so these spheres they meet along C perp, which I'm not drawing at the moment, but cutting something like this. Mm-hmm. Okay, and so we have sorry, this is cutting here. So we have some curve which comes out here, hits the point on C. And similarly, this cuts here. We have another curve. They close up. Okay. Okay, so each of these UIs, right, I cut by these spheres, and I have the external boundary on which I'm putting the Neumann condition, and then I have the internal boundary, which comes from these other two arcs, which are these, well, in the pictures are horizontal arcs, but they meet at the point on CPER. Okay. And so now we claim okay,
So maybe with respect to the boundary, you have drawn a rectangle there.
yes,
It's a topological thing, yeah.
yes.
Okay, the two boundary edges without any label, these are like circles or arcs of, no?
So the ones without labels
No,
are
internal geodesics.
internal geodesics, exactly, yeah. Yeah, so these are what I would call the vertical internal geodesics. Yeah, meaning they're on the.
And the other ones are the ones
Yeah.
containing the horizontal.
Yeah, exactly. So they're exchanged by, so if you want to draw, there's a great circle in here. And okay, yeah.
So
Yeah.
although I don't think you want me to use this, but the fact that you have angles, no?
Yeah.
But not every angle is. There is one angle in the upper right corner which is not pi over 2.
Let's see. Yes.
The other angles,
Yes.
I think they are pi over 2.
Yeah, that's true. That's true. Let's see. Actually, yeah. That's right. They're all pi over 2, corresponding to the fact that some of that is just from the symmetries, and I guess that these are pi over 2 because this k is 2. This k is 2. Yeah, but the end
when
it's not.
two of these
It's true.
horizontal planes where
Yes.
great circles meet,
Yep.
they meet of pi over n.
Yeah, you're right. Yeah, that's true. That's true. Yep. That's true. Okay. Yep. So now I claim that we can understand, compute the low spectrum for these subdomains, and then we can. So let's take that for granted for the moment, and then you can plug into the bound. So we get this information is implied that the index my u, which is right, this problem. Okay, but it's this domain together with the boundary conditions, right, which I didn't include in the notation to try to make it not too cumbersome. But here, this is going to be, yeah. So these two cases are distinguished by whether I put d on here or n on here, and so we'll have for the lower bound, this index is going to be at least. So we have the n minus 1. Sorry, how many domains do we have? I didn't mention it. Well, we're cutting by these m spheres of symmetry, and to help each sphere is going to hit C twice, and so we have 2n domains. 2n. So my n in the proposition is 2n. Okay, and we have, so in the first term, I look at just the index, but the index is 0, right? All of the pieces are congruent in this application. So I won't talk about them today, but we actually use also the proposition when you don't have congruent pieces. But here they are. Okay. And so here we're going to have 2n minus 1 contributions of 1. And the lower bound. Is going to be at most. So here instead, we have, so again, now we're using the different conditions, and so the spectrum shifts, but before the sum, I have the index plus the nullity, so that gives me a 1. And then I have 2a minus 1 other terms, which also give me a 1. Okay, so I know that the index is at least 2m minus 1, and this nullity is no more than 2m. So this in particular tells me that the nullity is going to be at most 1. But I claim that we definitely have nullity. So can you guess or not, or already know what Jacobi field is the right one to use here? So the last time we used JC, that was rotations about C or along C perp, and now we're going to use the other ones that we'll use the fact that we have J. C perp. Remember that this is, you could say this is rotations. So rotations, if I look at rotations about C, then these are going to have, so yeah, we'll look at these spheres of symmetry in a moment, but just to check, I didn't write it down. This is in B++. Okay, because if I reflect, right, I preserve the killing field and I preserve the normal surface. Okay, so it has the right symmetries. And it's a Jacobi field, so I know that the nullity is at least 1. Nullity is exactly 1, and then I get the index is exactly 2 minus 1. Okay. So then we have to study this problem now. Okay. Okay, so here we're looking at so I have MN and DD. So I'm going to impose the Dirichlet condition in the curves that I get when I cut these horizontal spheres of symmetry. Okay. JC perp. So JC perp satisfies the condition. It already satisfied the norm on I mean, we observed that just a moment ago, but it also is going to satisfy the Dirichlet condition on these spheres of symmetry, because if I reflect through one of these spheres, I reverse the killing field, but I preserve the normal to the surface. So JCC satisfies conditions. Okay, but by the same, so the argument that I tried to describe, the keywords are Alexandrov moving plane, right? Next method. We can do the same kind of argument. Again, you work on the Lawson disk, and now you look at starting with say the bottom face, and you rotate it and you reflect and you look for a first point of contact. We know you have a symmetry sphere, which is the bisector, but you prove through that maximum principle argument that you cannot that you must have graphicality up until then, because otherwise you have another sphere of symmetry, which we know we don't have. So is negative on this domain. So you have graphicality between consecutive spheres of horizontal spheres of symmetry for this field. Okay, and so it's non-negative. It's in the kernel, and so that's the first eigenfunction. So this shows. the fact that it has a sun finishes this. But, this is the answer. Yeah, for this problem. All right, so now we're going to look at the problem, the Neumann problem. It will be fully Neumann in this case. Okay. Okay, so we know that when we had some Dirichlet data, we had nullity, and so this problem will definitely have some index. And here, though, we're going to take advantage of this other symmetry, which is the fact that we have this great circle segment. Call gamma. Yeah, so in this region we have this is the point on C, and this is the point on C perp, and we have a great circle segment which joins them, which lies on the surface, and is a circle of symmetry. Okay. So I'm going to split this into two problems where I look at even and odd symmetry, and I just don't remember the notation, but okay. Okay. So this is UI, all the UIs look the same, and we're just going to split H1 UI. So we have even with respect to reflection through. Gamma, I mean, the great circle that contains gamma. Okay, so that will preserve, it is a symmetry of the surface, also the subgroup name. Okay, and it will preserve the boundary conditions. Okay, and so we can study the eigenvalue problem on these spaces separately, and equivalently, we can look at and here we either have Dirichlet or Neumann in here. Okay, and let's look at the Dirichlet problem first. And okay, and for this problem, what I want to do is, so I took this problem, I cut it up. Now I'm going to do an extension to another problem. So I want to take the problem on this domain, and I'm going to do reflection through these spaces. So instead, through the sides of the faces. So the faces, I mean the fact that these arcs lie on symmetry spheres, and so I do reflection through that, and I'm going to get we get a Lawson disk. So I mean a portion of the surface which is bounded by one of those quadrilaterals. Okay. Yeah, so I have gamma is going to be one of these one of these segments. So I'm looking at the Dirichlet problem. With even symmetries. I do reflection through the bisecting cubes. Okay, so I have that disk. And yeah, I mean, it's not hard to show from that. Sorry, if you think back to the graphicality plane, not from today, not the moving plane argument, but the one from the previous lecture where we looked at the uniqueness of the disk and we showed graphicality with respect to a certain Killian field. So we have the axis and we have graphicality. We showed along the axis, or the axis where the bisecting spheres intersect. Okay, so that means that we have a function which is non-negative, which has a sign on here. And it's not hard to conclude from that the Dirichlet problem on here, the first eigenvalue will be strictly positive. Okay, so so this was J. I don't remember what we called it last time, just J maybe. So this will be some circle L. So in the notation I've been using today, I'm talking about rotation about the orthogonal one, but it doesn't matter. This guy has a sign. And this implies that for this problem, it's going to be strictly positive. Because I have this function, which when I plug it into the operator, I get exactly 0, and that's a sign. And from there, it's straightforward to get. You have strict stability. Yeah, I mean, you can also say, well, the Lawson disk minimizes. So I get that the first eigenvalue is greater than or equal to 0, and you just have to get the strength. And that's very straightforward. So let's just say that. Okay. So we know then that for this problem, we get index and nullity are both 0. So yeah, the first eigenvalue is strictly positive. We'll leave it at that. Okay, and now we want to look at the Neumann problem. So now, okay. All right, so we know that the first eigenvalue will be negative. Neumann condition on all of these. That one is going to be strictly negative, but we want to show that lambda 2 is positive. Yeah, we want to show that the index, remember, for this problem is exactly 1 and the nullity is 0. And we've split this problem into the even and odd parts, and the odd part, there's no contribution to either of those. So if we can show that the index is going to be exactly 1 and the nullity is 0, then we'll be done. So this is what we need to show to finish this part of the argument. Okay, so to do that, so suppose, so consider now a second eigenfunction. And 2, so I'm going to get strong computer picture. And we know from the Courant nodal domain theorem, particularly the case for the second eigenfunction, that we have exactly 2 nodal domains. Okay, so there's going to be some nodal curve, and I know that the nodal curve what are the possibilities for the nodal curve? Let's see, the nodal curve must look like this or must look like this. One-sided. This is by triangle T. Okay, so we consider that in cases the various possibilities. So if my nodal curve okay, and so in each case, we can look at the cases in a moment, but in each case, if my nodal curve, maybe I'll just draw something like this. If my nodal curve, this is at least one of the sides, and then I know I can get, just by cutting off, get a test function for the same eigenvalue problem where you replace the normal condition by the Dirichlet condition. E for the miss. Okay, so in this case, I would look at the problem where I place this by dy, just because I have an eigenfunction. It vanishes here. I can extend then by 0. I cut off and I get another valid test function. It's an eigenfunction exactly, right? It satisfies the PDE in here. And so I know that I'm going to get a Rayleigh quotient, which is going to be give me the same lambda 2. And in this way, I get a test function for this problem. And we know that lambda 1 modified problem. And lambda 2. Okay, for the original lambda 2. So yeah, sorry, with different boundary conditions, right? This is the original on condition. This one is with the modified problem. Okay, but the point is though that we can handle all of those cases, so we have to consider separately. But actually, all of these cases have been tackled already by our previous work. Like this was the case that we did first, the odd case, so we already know. And the positive from the argument before we looked at the Dirichlet case, and this one. Yeah, for this one, so again, you can see this because you can do you can extend. So if you have an eigenfunction now for this problem, then you can extend by reflection through these spaces. Sorry, these spaces, and you're going to get an eigenfunction. Yeah, in this case, you're going to get, yeah, so this will extend. minus minus. I mean, I've forgotten now which side corresponds to what in the space, but the point is that by extending in both cases, you reduce to a case where you already know what the solution to the eigenvalue problem. But for one of these, you will definitely get b minus minus. In the other case, the considerations are similar, or you don't need to extend the whole space, but you extend to a situation that we've already tackled. And in all cases, we know that the first eigenvalue is going to be positive. And so this tells us that lambda 2 is also going to be positive or 0. So positive here, but actually in the other cases it could be 0. But that's okay for the argument. Okay, so sorry for not being clear about the extensions here, but the point is you do a nodal domain argument, and that's going to reduce to a case where you have extra Dirichlet, an extra Dirichlet condition, and you know that the first eigenvalue in those specific cases is going to be non-negative. And so the lambda 2 eigenvalue for the problem we're looking at with the Riemann conditions is strictly bigger. Okay, and that's putting that together, that's exactly what we wanted to do for the B++ case. I don't have too much time, but I already pointed out that the B plus minus problems are isomorphic. Okay, and so you can pick one of these and use JC for what I'm going to say. It doesn't matter, but I'll try to pick the right ones. Yeah. And so you can pick one of them, and you do similar things. You're kind of forced to work with these eigenfunctions because they have the correct symmetries, and you have to show signs for them on the corresponding domains. And there are further cuts to make too. So yeah, I don't have enough time to explain, but the idea is similar. So we need to establish. And for the most part, we use the same tools. So the arguments are somewhat similar. One difference is that we don't use maximum principal arguments for these guys. They're a little bit more intricate, but that's it. So maybe I'd better stop here. I've shown you most of the kinds of arguments that we use.
Is there any question? When you consider the general Lawson minimum surface, of course, how do you apply? Do you have more or less which is what is the result you can at this moment you can obtain in the Lawson general surface?
If you replace CG1 by CMK, yeah. So in that case,
what is the conjecture? Is there a conjecture for the
I'm not aware of a conjecture for the index.
Is not?
So yeah, you can do similar kinds of arguments. Yeah, there are a couple of challenges. Like one challenge is, I think, not very serious, is the fact that we use this first decomposition that I talked about with the two vertical spheres of symmetry. Is that if you have K being odd, you're not going to have two such spheres. I think so. That's a complication, but I think it's minor. The more serious ones is that when you try to do these kinds of arguments, like the one for V++, where you cut and you get a lower bound and an upper bound from your kind of argument, is that it's hard to see how you do that without a serious gap. So you can get an upper bound and a lower bound, but like what happens if you, yeah. So I mean, part of this work was inspired by thinking about the surfaces, and you can apply your argument in the case that you have the k equals 2 sharp, and you get exactly you can get the index exactly. But if you try to apply similar arguments for higher k, it's not clear how you can do that, and you have similar problems here.
Okay. So thank you, David. You did an incredible job for these 2 weeks. Just thank you again.
So another question is for this, this thing that you have mentioned about the shirt,
Yes,
the culture is all about this actually.
exactly.
So first, it should be, I mean, one should solve the case of cultures on other towers and then go to general Lawson.
I think that makes sense, yeah. I mean, there are significant differences, of course, things that happen, but yeah, I agree, I think that makes sense.